Today we are going to discuss some theoretical aspects related to drafting. First, an ideal structure of sliver. We are drafting sliver. Therefore, we first understand the structure of a sliver. Sliver is a random array of overlapping fibers. The sliver surface can be assumed to be a two-dimensional array of fibers. On the right hand side, you see that there is a schematic of fibers randomly placed within a rectangle which is representing the sliver. In each and every line there is a black dot at its tip. The line with the dot represents the fiber. So, the dot basically represents the tip of the fiber. Now, suppose we remove the tail part, that is the line part. So, we will be left with the dots. The position of the fibers are represented, let us say, by these dots now. Now, what we find in that rectangle is these black dots are randomly distributed over this rectangular area. So, fibers are randomly distributed as we can see them as dots on an area . Since the number of fibers are large, probability of a fiber end, that is a dot appearing in a strip of length d l as shown in the lower diagram d l will be very low. The number of dots appearing in d l will therefore follow Poisson distributions. Let x be the number of fibers in the element d l. Then we can write that probability x is going to be n as e to the power minus n capital N to the power small n divided by capital N. This formula is coming because the fibers are following Poisson distribution. So, this is the density function of Poisson distributions, where capital N is the average number of fiber ends in the sliver cross section and small n could be 0, 1, 2, 3. So, this is how we can describe statistically the arrangement of fibers in sliver. Once we understand the way the fibers are distributed and they are all following a Poisson distributions, now we can find out, because of the Poisson distribution, what could be the irregularity in their number. And this irregularity, because of this randomness in the distribution of fiber, is known as minimum irregularity, and this is also known as limit irregularity. So, let the average number of fibers in the cross section be capital N in case of Poisson distribution. The standard deviations of the number of fibers in the cross section should be sigma will be 1 upon root n. That is this thing we get because the fibers follow Poisson distribution, and hence the CV is always sigma by m into 100. So, if the standard deviation is 1 upon root n, sorry, this will be n, capital N. Therefore, Cp will be root over n by capital N. So, if we take the ratio Cp percentage root over n by capital N into 100, then we get it 100 by root n. That becomes the minimum irregularity in the number of fiber ends that we can expect in a sliver. This irregularity is minimum and therefore, is also known as limit irregularity. That is, the actual irregularity of a sliver cannot be less than this, and the irregularity in the number of fibers is directly associated with the irregularity in the mass per unit length also. Therefore, we say that the minimum mass irregularity will also be similar to 100 by root over n. Now, we discuss an interesting model of drafting based on pure geometry. In the diagram on the right hand side, what we see here, that there are two vertical lines and these two lines are indicating front roller nip and back roller nip, all right. And now, the front roller nip means these two rollers which are here is moving at a speed of velocity v 1 and the back rollers are moving at a velocity v 0. The distance between the two nips is equal to capital L, that is length of the fiber, and this distance is also known as ratch. There are two fibers shown here and these two fibers are represented by a blue line and an orange line. The blue line, if you see, it is a little longer than the orange line. So, blue line is a little long fiber and the orange line is representing a small fiber, a shorter fiber. The other thing is that at the beginning there is a difference in the ends of these two fibers, that is the blue and the orange, and the distance between the leading ends of these two fibers is represented by y bar, that is the shear, we call it shear before drafting. These two fibers as stage 1, what we can say that both of them are moving at the velocity v 0, because both are gripped by the back roller nip. Hence, both are under positive control of back roller, and hence at this moment, that is stage 1, both of them move at the velocity v 0, and therefore, whatever is their relative position, this relative position is not going to change. From here we go to the stage 2. In stage 2 is a stage where the short fiber is about to be released from the back roller nip. So, if you see the orange fiber, the tail end of the orange fiber is just lying on the back roller nip. Therefore, the fiber is about to be released, but the long fiber, that is fiber B, which is represented by the blue line, is under positive control of back pair of rollers, and therefore, it is moving at the speed of back roller. Now, at this moment, when the short fiber A is about to be released from the back roller nip, it has to travel a distance A, which is we call it floating distance, to reach the front nip. So, time taken for the short fibers A to reach the nip of the delivery roller or the front roller nip will be how much? This time represented by T, which is A by u, and what is u? U is the average floating velocity. So, once the fiber A leaves the back roller nip, it has to travel a distance a, and during this journey we are not very sure about its speed, and we assume that it runs at a speed of u. Therefore, the time it takes to reach the front roller nip or the delivery roller nip is going to be a by u. Now, once this reaches the front roller nip, stage 3, if we see, when the fiber has just reached the nip of the front roller, B, the long fiber still continues to move at the speed of v 0. This fiber is long and its length is equal to the length of the ratch, that is nip to nip distance. So, it continues to move at the speed of v 0. So, time taken by fiber B to reach the delivery roller nip from the time fiber A starts floating. So, fiber A starts floating at the stage 2 and it takes time to reach the front nip, which is a by u. From this moment onwards, fiber B starts moving towards the nip, and how much time it takes to reach the front roller nip. That time is going to be y bar plus a by v 0, because if you look at the diagram, you see that the time from the time at which A starts floating, at that time the position of the fiber B is such that the distance between the leading end of B and the nip line is a plus y bar. Therefore, it has to travel this distance, but this fiber is moving at the speed of v 0, and hence the time it takes to reach this is y bar plus a by v 0. Now, let us t 2 be the time taken by fiber A to change its position from stage 3 to stage 4. Now, let us go from stage 3 to stage 4. So, at stage 3, at the end of stage 3, the fiber A has just reached the front roller nip. So, now onwards A will continue to move at the speed of v 1, that is, we are certain about the speed of A, that is the short fibers. During this time, the fiber moves at the speed of v 1. So, therefore, t 2, which is t 1 minus t, and that will be equal to how much? This is equal, if we put the value of t 1 here, is y bar plus a by v 0 and t is a by u. So, we get t 2 as shown in the equation. Distance moved by the fiber A during this time t 2 will be y 1 bar, and that is will be v 1 into t 2, and hence it is going to be as shown in the last equation. So, during this journey, the fiber A, short fiber, continues to move at a definite speed of v 1. So, you see that how far it will move during the duration t 2, and if you simplify this, then we get v 1 by v 0 y bar plus a into v 1 by v 0. You can all do it, and what is v 1 by v 0? That is the draft. So, we replace v 1 by v 0 by z, where z indicates the draft. It becomes z y bar plus a z minus a into v 1 by u, and if we take z common, then that becomes z y bar, and we take a common from these two, it gets a into z minus v 1 by u, which will be, we can write z y bar plus alpha. We represent alpha to be z minus v 1 by u. So, the distance between the leading ends of the fiber A and B after drafting is going to be z into y bar plus alpha. Alpha is known as a deviation from normal shear and is a source of irregularity. The normal shear ideally should have been z y bar, that is, the distance between the ends of the two fibers after drafting would be z times, that is the draft times their distance prior to drafting, but we get an additional term alpha, and therefore, we say that there is some deviation from what ideally one should expect, and this part of the deviation we call is deviation from normal shear. Ideally, the distance between the leading ends, that is the normal shear, would have been z y bar. However, due to floating velocity of short fiber A, the distance become z y bar plus alpha. So, alpha indicates an irregularity in the placement of fibers in the sliver after drafting. Now, how to make alpha 0? If we can make alpha 0, then we cannot expect any irregularity into the drafted product. So, if we look at this mathematical equation, then we can say that if u is V 0, then alpha becomes alpha mean, that is equal to 0. If I replace u by V 0, then it becomes V 1 by V 0, and V 1 by V 0 is capital Z, which is draft, and therefore, it becomes Z minus Z, it becomes 0. So, deviation from normal shear becomes 0. So, in that case, we may expect no irregularity to be generated because of the floating velocity of the shorter fibers. The other extreme is u is V 1. In that case, the value will be a into z minus 1. Hence, alpha varies between 0 to a into z minus 1. So, this is how the deviation from normal shear can vary between 0 to a into z minus 1. So, alpha represents the irregularity generated due to drafting as a consequence of uncertain movement of the fibers, especially the shorter fibers in the draft field. So, fibers which are shorter, any fiber whose length is less than the length of the draft field or the ratch, we can say these are the short fibers within the drafting zone, and when the short fiber is passing through the zone, there is a chance that they may move in a very in a manner which is neither V 0 nor V 1. They will take up some intermediate speeds, and because of this their placement within the drafted product is going to be very uncertain in nature, and hence there could be development in irregularity. And the only way to minimize is to compel the short fibers to move at the back roller speed till they reach the front roller nape. That means, if I can make u the floating velocity to be V 0, that is floating velocity is equal to the back roller speed, in that case the irregularity that will be generated will be minimum. So, that is one of the effort the designers of the your drafting system has been trying to ensure that the short fibers are made to move as far as possible at the speed of back roller till they reach the front roller. Okay. So, I hope this is clear now. Now, we will discuss the theory of draft distributions. Now, in the draw frame, you see there are basically two zones are there for drafting this sliver. One is the main zone, the other one is the back zone or break draft zone. Whatever is the roller arrangement, ultimately the drafting system has two zones of drafting. The question comes that what should be the draft in the back zone and what should be the draft in the front zone. How do we distribute the draft? If I say we want to keep a draft of 6 or a draft of 8, then how much we should keep in the front zone and how much we should keep in the back zone. This is what we should try to find out. Now, there is a simple theory which is based on the theory that we have just discussed now, and let us going to understand this distribution theory of draft. Shear after drafting in the back zone as stated earlier is going to be Z 1 y 0 bar plus alpha 1 bar, and shear after drafting in the front zone is represented by the next equations. So, how much is going to be the shear, that we have already discussed, and so let us say the back zone shear is y 1 bar, the average front zone shear is y 2 bar, and the equations are similar, where Z 1 and Z 2 representing the draft in the back zone and draft in the front zone. So, if the y 2 bar is the shear after drafting in the front zone, so in the y 2 bar equation, if we replace y 1 bar as shown in the diagram, as shown in these equations, and you simplify it, then we can see that y 2 bar is going to be this, that is y 0 bar z plus alpha bar. So, where z is z 1 into z 2, the z is the multiplication of z 1 and z 2. If the drafts in the two zones are z 1 z 2, the total draft is going to be multiplication of these two individual drafts, and alpha bar is also shown here. So, alpha 1 bar and alpha 2 bar average deviations, that is average deviation as stated earlier, the deviations from normal shears. Let us say these deviations are standard deviations. Being standard deviations, they should be proportional to their ranges, that is the maximum value of the shear in this case, and it has been shown previous section that the shear, the minimum shear is 0 and maximum shear is going to be A into z minus 1. So, alpha 1 and alpha 2 can be written as, because they are proportional to the range, k A into z 1 minus 1 and alpha 2 bar is k A into z 2 minus 1, that we can write because they are proportional to the respective shear. To keep the irregularity minimum, the deviations should be equal to 0, that is the final total deviation, which is alpha bar, should be 0. So, if we put alpha bar to be 0, then we can write z 2 alpha 1 bar plus alpha 2 bar is going to be 0. The next equation we write z 2 into alpha 1 bar minus alpha 2 bar equal to 0. Why I am writing alpha 2 negative here? Because unless alpha 2 becomes 0, become negative, the sum of these two cannot be 0. So, deviations are not only positive, deviations could be negative also. This is fact one have to remember in mind, because if we define the position of a fiber not by the leading end, but by the center point of the fiber, in that case it is possible that the deviation from normal shear could be sometimes positive, sometimes could be negative. This is what is possible, and therefore, if I want to make alpha bar 0, then z 2 alpha 1 bar minus alpha 2 bar has to be 0, where alpha 2 bar is basically negative shear, and we substitute the value of alpha 1 bar in this equation and value of alpha 2 bar also in this equation. Alpha 1 bar has been stated on the top, and alpha 2 bar also has been stated on the top. Just substitute and then simplify. If we go step by step, we will find that you are getting an equation where k a into z 1 z 2 minus z 2 minus z 2 plus 1 is going to be 0. Now, there are two options, either k is equal to 0 or whatever is there within the first bracket, that is going to be 0. If we put z 1 z 2 replaced by z, because that is the total drop, 2 z 2 plus 1 equal to 0. From here we can write that z 2 is going to be z plus 1 by 2 and z 1 is going to be 2 z by z plus 1. So, we can find out the values of z 1 and z 2 if z is given to us. Now, accordingly, what we have done, based on this formula, we have found out what could be the drafts for two situations where the total draft is 6 and 8. So, in the case of total draft 6, the back zone draft calculated based on this theory is 1.71 and therefore, the front zone draft becomes 3.5, and if we multiply these two, we will get 6. If the total draft is, we keep it 8, then the back zone draft is going to be 1.77 and the front zone draft is going to be 4.5. So, we see that this theory can give us some idea about the distribution of draft in the two zones, so that we can minimize the generation of drafting irregularity. Though we must know that in the actual practice there could be some more factors which will also come into play. The theory is only based upon some idealistic situations, but in the actual practice that could be many other factors which we have not taken into consideration in our theory development. Therefore, the draft that we get based upon the theory can be considered to be as a initial estimate of the draft, but the final value of draft has to be decided based on actual experimentations, because there are so many other factors like fibers are not straight and parallel, fibers are hooked and looped, fiber to fiber differences could be there in terms of their frictional property, their crimp, the actual your stress strain behavior of the fibers are different, because many other factors will come into play, and therefore, we can say that the actual draft that we practice in the industry may be little different than what we get based on the theory. But theory helps us to understand that how the draft can be distributed and what is the logic that we can apply in deciding the draft in the back zone and in the front zone. The next interesting part is the drafting wave. The fibers in sliver are neither of same length nor straight and parallel with respect to sliver axis. This we have to know that the fibers in a sliver are not of all same length. There are short fibers, long fibers, medium length fibers, everything get mixed. They are not straight, they are not parallel to each other. The nib to nib distance, that is the ratch between the rollers, is set close to the longest fiber. We always try to keep it close to the longest fiber, because we want to make sure the long fibers do not get stretched and break while the fibers are being drafted together. Many fibers always remain shorter than the ratch, as stated earlier. There will be, in the case of cotton especially, there will be many fibers which will be shorter than the ratch. This can also happen with synthetic fibers, because the fibers remain in a folded state in a card sliver. So, many of the fibers, even though actually they are long, but because of they remain in a folded state, in a hooked state or in a loop state, therefore, their actual extent may be much less than the ratchet. Now, all these short fibers, the fibers which are shorter than nib to nib distance, remain in a floating state, and they are neither gripped by back rollers not by the front rollers, and hence move at an intermediate speed, because once they are released from the back roller nib, the fiber has to pass through a distance where they are not under positive control of any of the rollers, and therefore, we know that they will be keep moving, but we are not very sure about their speed. The only thing that we are sure is this, that their speed is going to remain between V 0 and V 1. This cannot be less than V 0, cannot be more than V 1. It will take some intermediate speed, but that speed is completely uncertain. Now, this diagram gives a visual statement of whatever I have stated, and we see that the orange color fiber is a shorter fiber. It is surrounded by many other fibers and passing through the drafting zone. So, at the beginning, the short fiber is gripped by the back roller and therefore, moves at a uniform speed of V 0 till the back end of the fiber is released from the back roller nib. Now, once it is released from the nib as shown in stage 2, it is yet to reach the front roller nib. So, during this journey, their speed is completely uncertain in nature. This fiber is surrounded by other fibers which are moving at a speed of either V 0 or V 1. So, the fiber is in contact with slow moving fibers as well as with faster moving fibers. At any location, how many fibers surrounding this particular fiber are moving at back roller speed or at front roller speed is very difficult to determine accurately, but roughly we can say that as long as the short fiber, the floating fiber remains closer to the back roller nib, but not nipped by it, most of the surrounding fibers will be moving at the back roller speed, because closer to the back roller nib, majority of the fibers will be moving at the back roller speed. But as it moves forward and going closer and closer to the front roller nib, the fibers surrounding this floating fiber will be mostly moving at the front roller speed. So, the nature of fiber surrounding this short fibers or floating fiber keeps changing from the back to the front roller nib. In the stage 3, what we see, the fiber has almost reached the front roller nib. The dominance of faster moving fibers becomes overwhelming and the fibers start moving at the front roller speed. So, by the time it reaches almost to the nib, maybe may not have been gripped till now, but as of now in this particular situation in stage 3, we see that the fiber is yet to reach the nib, but is very close to the nib. Majority of the fibers surrounding this fiber in this location are all moving at the front roller speed, and therefore, the influence of the front fibers moving at front roller speed will be overwhelming on it, and all of them will try to drag the fiber at their speed, that is at the front roller speed. This is how the journey of a fiber takes place, from back nip to front nip, and what happens as a result is this, that when the fiber is coming closer and closer to the front roller nip and it starts moving with the front roller speed, but in the intermediate region we are a lot of uncertainty about its speed. Once a particular fiber starts moving at a higher speed, it will influence others with which this is associated or it is in contact, and many of the neighboring fibers will be influenced by this fiber, and it will also try to drag some fibers along with it at a higher speed. And as a result, what happens, there are accumulation of floating fibers along the length of the sliver, and wherever there is accumulation we get a thick region, and once there is accumulation of fiber in some places, that automatically means that there will be a region very close to it from where many fibers have been influenced, and that speed has suddenly changed, and therefore this region will be devoid of fibers also. So, if there is accumulation here in this region, there will be depletion of fibers. Hence, accumulation and depletion will occur in a cyclic manner. Therefore, there will be zones where there will be increase in mass, and there will be zones where there will be fibers will be less in number, there will be thinner regions. So, thick and thin regions will occur simultaneously, and this is what we call a kind of wave formations. We call it drafting wave, where there will be accumulation of fibers, mass is more there, and there are regions where the fibers are less, and these regions will be thinner, and hence thick and thin regions will occur in the drafted product, and this kind of waves sometimes are very visible with our naked eyes, and this we call drafting wave, is a kind of irregularity into the product. Some regions are devoid of fibers, and in some regions we have excess fibers. So, all this is happening because of some fibers are influencing some floating fibers to move along with them, and a chain reaction starts. One or two excess fibers in a particular region moving at a higher speed will also try to influence the fiber which is in contact with this fiber, and this chain reaction will occur. Suddenly, from a region shorter fibers will move forward together and create a thick region. The wavelength is of this mass variation, lambda is almost close to 2 LF, where LF is the average fiber length. In the diagram here, the uncertainty of speed that we have discussed is shown here, that from back nip to a certain distance, the floating fiber is moving at a constant speed as it enters the back nip, and then there is a region where the speed is fluctuating. Sometimes it is influenced, speed goes up, contacts breaks, speed may go down. So, there is a fluctuation in speed and there is uncertainty about your speed. So, this is basically V 0 and this is V 1. So, there is a time when we are not very sure about the speed, that is what is being represented in this particular diagram. All right. So, this is how the drafting wave gets generated, and due to this we get irregularity into the drafted product. Therefore, the source of drafting wave is the presence of floating fibers or fibers shorter than the ratch. So, as long as we have fibers shorter than the ratch in any drafting zone, there will be some drafting wave in the delivered product. We have to always try to reduce the amplitude of the drafting wave, and hence we must know that what are the factors which affect drafting wave. If we know the factors and the way they affect, then we will be able to suggest some methods to suppress the drafting wave. So, the factors are listed here. The intensity of the wave depends upon draft, the magnitude of the draft, the fineness of the sliver, the number of doublings, that how many slivers we are combining, the roller setting, the degree of parallelization of fibers, and proportion of short fibers in sliver. All of them will affect the intensity of the wave or the amplitude of the wave. First, the effect of draft. What is the role of the magnitude of draft on drafting irregularity? The intensity of the wave is measured in terms of the relative variance, that is the square of CV. Now, here the diagram is shown. One side x axis we have draft, on the y axis we have relative variance, and we see the three lines are shown here, and we see that as we go on increasing the draft, the relative variance is increasing, and as we go from coarse to finer sliver, the slope is becoming more and more. This equation of this line is represented by a straight line, because it is very linear in nature. So, the relative variance added due to drafting is A into d minus 1. CV percentage of due to drafting wave, therefore, will be root variance is A into d minus 1, and therefore, CV is going to be root over the variance. So, it will be A root over A into d minus 1, and therefore, we can write this equation, that CV square out is CV square in, that is CV of the input material, and multiplied by A indicates the slope, into d minus 1, that is what is the draft. If d is 1, the draft 1 means there is actually no draft. In that case, the right hand part will be 0, and CV squared out and CV squared in, and the input and output they will be all same, because when the draft is 1, there is no drafting at all, and draft cannot be less than 1. So, once we give a draft of 2, 3, 4, 5, then we see that with increase in draft, the relative variance is going to be more and more. That means, any drafting operation will always add some irregularity to the drafted product. The slope will change depending upon the fineness of the sliver and the nature of fibers within the sliver. Now, effect of sliver fineness. Fineness in a fibers in a sliver are drafted in the form of independent strips as sub slivers. It has been shown by taking photographs that the fibers in a sliver are drafted in the form of independent strips, as if a sliver is made of thin strips of fibers, and in these strips are drafted independently of each other. The drafting wave is generated in each of these sub sliver independently, and the thick and thin regions of the sub slivers do not coincide with those of the neighbors. They remain out of phase with respect to each other. This point is most important, because visually it has been seen that if the strips get drafted independently to each other, then each strips have their own drafting wave getting generated, but the thick and thin regions on each of these strips are also independent in nature. So, not necessarily the thick part of one strip will match the thick part of the neighboring strip. It may match, it may not match, most of the time it does not match, they remain out of phase. That is why the thick and thin places in the strips therefore compensate each other. Hence, if there is a thick region in one strip and in the neighboring region, in the neighboring strip I find a thin region, and thick and thin regions will try to compensate each other. The sub sliver formations will be more in number with coarser sliver. So, while drafting coarse slivers, we will have lesser addition of CV or irregularity. Thus, the doubling effect is more for coarse sliver in comparison to the fine ones. Hence, with increase in fineness of sliver, the sliver will be more irregular. That if we make the sliver fine, then we can expect more irregularity into the drafted product. So, in a way therefore, thicker slivers are better, because we will get a doubling effect within slivers. Then comes fiber parallelizations, that is the role or state of fibers within the sliver. And you know that card sliver, all the fibers are highly deformed, they are not straight and parallel. So, parallelization is less, but if I feed a sliver which have been already passed through the draw frame once, then there will be improvement in the parallelization of fibers, the reduction in hooks. So, this sliver we will see is going to be a better in terms of drafting than the sliver which contains lot of non-parallel fibers. So, with increase in parallelizations along the sliver axis, the fibers slide past each other smoothly in the drafting zone. So, the interference between the fibers will be much less, because they are all straight and parallel. Otherwise, one particular fiber which is moving, it will interfere the neighboring fiber, because it is in contact with others, and that will cause irregular movement of the fibers within the drafting zone. Effective length of all fibers also improves due to improved orientation and reduction in hook extent. It was also told to you earlier that the fibers in the sliver, even a fiber may be long as the ratch, but if it remains folded or if it is hooked, then the effective length of the fiber is actually less than the ratch. Then this fiber, even though actually long, will behave like a short fiber. Therefore, with synthetic fibers, even though to start with there is no short fibers there, but still with synthetic fibers there is a possibility of development of drafting wave, especially in the case of card sliver, because lot of fibers in the card slivers are in folded state, and hence the effective length is short. So, fibers may not be short actually, but because of their configuration they are shorter and behave like a short fiber. So, if we can parallelize the fibers, if we can remove the hooks, then proportion of short fibers within the drafting zone will be less, because of better orientation and reduction in hooks. So, therefore, with such sliver we expect less irregularity. Hence, parallelization and orientation of fibers within the sliver is going to help in terms of making the drafted product more regular. Next comes effect of setting. In the case setting, we basically mean the ratch distance between two nips. So, fibers are released from one nip, they travel through a drafting zone and then finally get nipped by the other nip, and then it moves out of the drafting zone. Irregularity decreases at first. If you look at this diagram, we see the irregularity in terms of CV percentage first going down, becoming minimum and then rising again. The minimum is obtained at a setting less than the maximum fiber length. In the case of cotton, we have fibers starting from 4-5 millimeters to let us say 51 millimeters, because we have shorter fibers, we have long fibers. We all know in the case of cotton it is a mixture of fibers, and the minimum CV is obtained when the setting is just less than the maximum fiber length. But we do not keep the setting at this level in the actual industrial practice. Why? Because at the closest setting there is a chance of spewing or undrafted sliver or looping to be produced. That is, since in this setting it is little less than the maximum fiber length. The maximum fiber length fibers of that category could be 2%, 3%, 5% in nature. So, even though I am holding 2, 3, 4, 5% fibers simultaneously by the nip of back and front roll up, still it may not result in too much of irregularity. So, we may keep a distance which is little less than the maximum fiber length, and we get minimum irregularity into the drafted product. But still we want to avoid it, because we never know that in a given cross section what percentage of fibers in that cross section is actually longer or equal to the maximum fiber length. So, in the population that could be 2% or maybe 5%, but when the fibers are moving through the drafting zone, there have already been lot of mixing has taken place, but we are not very sure how the fibers, long fibers are distributed within the sliver. So, there may be a situation when a particular cross section comes and gets drafted, a number of fibers, especially max long fibers, may be more than 2% or 5% fibers, and in that case there is a chance of spewing. That is, when fibers are knit by both the grip both the rollers and pulled forwards, they are not getting drafted, they are basically stretched, and this situation is known as spewing, that we will get undrafted ends. So, the risk of getting undrafted ends is more when we observe a setting which is little less than the maximum fiber length. So, to avoid spewing, what we do? We keep a setting which is somewhere here. We move from minimum to slightly on the higher side, so as to avoid spewing, because unknowingly spewing will be there, we will not be able to always see it, and therefore, undrafted material will move forward and that will give me yarn fault. At the same time, if we keep the distance too much, then also the material will be highly irregular, because most of the fibers will behave like short fibers. So, if the setting or if the nip to nip distance is too large, majority of the fibers will behave like short fibers, and they have to travel a longer distance, and hence possibilities of development of drafting wave will increase, the intensity also will increase, and therefore, this material will be or the sliver will be more and more irregular if the setting is too wide. effect of doubling. Okay. What happens if we increase the number of slivers in the input? Individual slivers are drafted and the drafted wave is combined at the delivery end. All right. The CV of the combined slivers at the output is expected to reduce following the doubling rule as shown by these equations, that CV of combined CV will be CV of the output by root n, CV of the material in the output, if we n of them are combined together. So, the net will be CV out by root over n, that is going to be the combined CV of the output slivers. Now, if I write this in the form of equation, CV squared out it will be CV square in into A into d minus 1. This equation we have already learnt earlier, that draft is the, you see the draft D is coming into the picture. Why it is coming into the picture? We will now going to explain that with the increase in doubling, draft has to increase to keep the sliver hang at the same level. So, if I go from 4 slivers to 6 slivers, the input bulk is more. So, therefore, to keep the output sliver linear density same, I have to increase draft. So, more doubling means more draft too, and hence if the draft is more, we have seen there will be an increase in irregularity. So, what we see, there is a positive influence and there is a negative influence on irregularity because of doubling. One, the doubling is more means compensation between the slivers is going to be more, that is irregularity compensation, and therefore, we can expect the sliver to be more uniform because of doubling. At the same time, if I go for more doubling, draft is going to be more, and additional draft means more, means it will generate more irregularity in the product. So, therefore, the effect of increase in doubling and draft opposes each other as far as the irregularity generation is concerned. The net depends upon which one is predominating, which effect is predominating in nature. Till the doubling of 8, an increase in doubling reduces the output sliver irregularity. That has been found with the modern draw frame, and instead of going from 5 doubling 5 draft, 6 doubling 6 draft, if we go up to 8 doubling 8 draft, we actually expect the irregularity to go down. The other advantage we get, even if the irregularity does not go down, improvement in parallelization. More is the draft, more parallel the fibers would be in the output. That also we have to keep in mind, that why we will try to go for higher draft and higher doubling, that also happens. But you have to remember that both the things are simultaneously occurring, and hence the net effect is what we get. So, initially the increase in doubling up to doubling of 8, there is an improvement in irregularity. Next is effect of proportion of short fibers. For a fixed setting, if the short fiber proportion in the input sliver increases, then what is going to happen? The more the short fibers in sliver, more will be the average floating distance, and hence more irregular motion of short fibers is expected. Irregularity is produced depends upon the coefficient of floating represented by B, where B is R by L bar minus 1 whole square plus CVL square. So, CVL is the CV percentage of fiber length, R is the ratch length, and L bar is the average length of fiber. So, this has been a numeric, this is a equation which is an empirical equation, and we see here that if the short fibers are more, that means Cb of fiber length also will be more, and therefore, your coefficient of floating value is going to be more, and that means more irregular the sliver would be. The physical reasoning is quite obvious, that if I have more short fibers, then there will be more floating fibers. So, many fibers will move in a very erratic manner within the drafting zone, and therefore, more irregularity will be generated in the drafted product. And hence, if we compare, we will see that if we draft combed sliver and we draft carded sliver, we will see in the case of combed sliver, the irregularity generation is less. Why? Because by combing we have removed a lot of short fibers are less there, and hence there will be improvement in terms of the additional irregularity that is generated is because of due to drafting. We discuss another aspect, which is roller eccentricity. The drafting rollers not necessarily will be concentric, they are supposed to be concentric, but because of many reasons the rollers may be eccentric, that is their center of rotation and their geometrical center may not match, we call it eccentric roller. Whenever for any roller its geometrical center and the axis of rotations are not same, then we say it is eccentric roller. Like in this diagram, the black dot is indicating the rotational axis of rotation, whereas its geometrical axis is here at the center of the roller. So, they are not matching, and hence we say this roller is eccentric in nature. Now, what happens if this roller is eccentric in nature? This is basically a manufacturing defect of the roller, or with time it may also happen with such rollers, some rollers. The velocity of the input roller, let us say take a simple case where there is a single drafting zone having 4 pair of rollers, all the rollers are of same diameter, but their speeds are different. It is a drafting zone, and therefore, front rollers must rotate faster than the back rollers. The velocity of the input rollers is 2 pi n 0 dr by 2. So, roller diameters are of dr, and therefore, velocity of the input roller is 2 pi n 0 dr by 2. This will be surface speed of the roller. The velocity of the bottom front roller for two different locations is shown here in A and B. In A, we see that the axis of rotation is below the geometrical axis of the geometrical center of the roller by an amount epsilon, and therefore, at this particular stage or A, the surface speed of the roller is going to be 2 pi n 1 dr by 2 plus epsilon, because the effective diameter has changed. The distance from here to this is dr by 2 plus epsilon, and therefore, surface speed at position A is going to be as shown in this equation. When in position B, the axis of rotation is just above the geometrical axis of the roller, and in this location the speed is going to be, surface speed is going to be as shown in this diagram, that is it will be 2 pi n 1 dr by 2 minus epsilon. So, and in any other location the speed, surface speed is going to be in between these two extreme limits. So, n 0 is the rotational speed of the input roller, n 1 is rotational speed of the output roller. Now, in these two locations, what is going to be the ratio of the surface speed? Ultimately, the surface speed ratio is the draft, mechanical draft. So, if we find it out, then we will find that in position A, just take the ratio V A out by V in, and you will get this value as shown here, n 1 by n 0 1 plus 2 epsilon by d r. In position B, it will be exactly same, only thing is this, that it will be 1 minus 2 epsilon by d r, rest of the things will remain same. That means, the ratio of these two is the draft, and therefore, what will happen? The draft is cyclically going to change for each and every revolution of the bottom roller. Draft is not constant. That is the effect that we will get if the rollers become eccentric. Length of the sliver that is delivered per revolution of the bottom roller is always pi d r. The draft will vary in a cyclic manner over every revolution of the bottom roller, and a periodic mass variation will be introduced with an wavelength pi d r in this case. So, this will lead to periodic variation in mass, because the draft is cyclically changing, and that will lead to an error in terms of mass variations, and this percentage error is shown by this. This will be plus minus 2 epsilon by d r into 100. So, this is all going to be the effect of eccentric bottom roller, and that is eccentric front bottom roller. Now, if the other rollers are eccentric, what is going to happen? If the back roller is eccentric, suppose the back bottom roller is eccentric, what is going to be the effect? We will have similar variation will be generated. However, the wavelength of variation is going to change, because if the back bottom roller is eccentric, then the wavelength is going to be multiplied by the draft in that zone. If the draft is z, then the wavelength of variation is going to be pi d r z, where z is the draft in this zone. Wavelength will change, but the intensity of the error will remain same. From there, if we go to the top roller being eccentric, no error will be produced, as top roller surface speed does not change, being friction driven by the bottom rollers. This is what we have to remember, that if the top roller becomes eccentric, draft is not going to change at all, because top rollers are surface driven. There is no independent drive we give to the top rollers. They receive their drive because of friction between the bottom roller and top roller, and hence their surface speed is not going to change, even though their effective diameter is going to change, because being eccentric. That means, the bottom roller becoming eccentric is much more dangerous in nature than top rollers being eccentric. The causes of eccentricity are bending of bottom rollers because of too much of pressure which is acting on them. So, with time this might happen after 2, 3, 4, 5 years, these possibilities are there. Improperly mounted or poorly made gears and manufacturing fault in the bosses of top roller. It can also happen for top rollers, but as I said, even if the top rollers are eccentric, it is not going to create problem as far as the change in draft is concerned, but it can create some other problem, which we will also study later on, that if the top roller is eccentric, what problem may arise in the drafted product. But as far as the draft is concerned, eccentricity of the top roller is not going to affect the draft. With this, we close today's lecture, and thank you.